Hello everybody, bienvenidos todos. Welcome to a new session at Quantum-Latino. Now we welcome Dr. Nariman Saadatmand from QuantumBrilliance. He will address the lecture Quantum Accelerator, a new trajectory for quantum computing. So let me, Nariman, excuse me, let me introduce you to the audience. Nariman Saadatmand has over a decade of track record in the quantum computing industry and academia. Nariman has developed hybrid classical quantum algorithms and software platforms based on tensor network and machine learning tools, including XACC, Qiskit, and TensorFlow. He previously led the development of open source C++, Python, and MATLAB toolkits, where he acquired a deep understanding of software life cycles, pipeline tests, and release support. Nariman has extensively used project management and version control tools and published several high-impact papers and product testing reports demonstrating his expertise in quantum information theory and scientific software development. Nariman, welcome to Quantum-Latino, and the floor is yours.
Thanks, Rafael. Thanks for the extensive introduction. Well, as Rafael said, my name is Nariman Saadatmand, and I am the Quantum Application and Software Lead in QuantumBrilliance. Let me start by thanking Rafael and Quantum South and all organizers of Quantum-Latino. It's a real pleasure to have the opportunity to introduce to you all the unique vision we have for quantum, which, as you can see on the screen, is quantum accelerators. So let's get to it. So who is QuantumBrilliance? So we are the first and the world leader in building room temperature quantum computers using Diamond MV centers. So, and where it got started, it was actually in 70s because we are a spin-off out of Australian National University when they commenced the Diamond MV Center research program. And the work started, really pioneers in solid-state physics. They worked to first show quantum computing is possible using MV centers, and then later to demonstrate that quantum control is possible. But after early 2000, really the work stopped. And the challenge was that, okay, that's great, but how to scale up really? And this is where our founders come into action. So Marcus Doherty and Andrew Horsley, two of our founders, they were people who pioneered that and proposed that how could you actually scale up the MV centers to have more than 1 qubit. So we're coming to the 2019 now, when the QuantumBrilliance officially incorporated, and we won several startup awards here in Australia. And then in 2020, we were featured as a national leader in quantum computing, coming to June 20, where we closed our funding round, initial round, and then started construction in Canberra. Later that year, we were the first to secure government funding, and we opened up our headquarters in Germany, which we are very proud to work with major German partners. As you can see, some of them are on the screen, including Fraunhofer, IF. And then to the December 20, when we actually partnered with several quantum application companies. This include Quantum South, very proud of collaboration there, but Trillis Data, machine learning company, QAR Lab in Germany, and other LMU companies. So 2020, start of 2020, world leaders in Diamond Quantum Computing joined our advisory board, and we actually hired our 18th employee. Today we building room temperature quantum computers, and we have close to 20 employees, which we think they are best of the best. So, but what's available today, 2021, it's what we call the Quantum Development Kit. It's the standard 1U rack, 19-inch rack you could see in all HPC centers. It's that size. So this really, it's important to notice this is not designed to scale up. However, it's enabling experimentation with possible integration with HPC system. So this is the one that we are currently delivering to the PASI HPC Center. It's give you the opportunity how to integrate a quantum computer, host on site, and build and test co-processing application. What we are going in 25 and after that is to build, to actually put all these in a GPU card size. So it would be as much as any graphical card size you see every day. So this would deliver quantum utility. We are aiming for around 50 qubit on that. It would be integration ready with your classical systems and would support unique application, parallelization, and edge computing. So, but how's our ecosystem looks like? On your left, you could see like a vision of the system. So when we talked about our hardware system, it actually have several layers. Obviously, it's quantum bus first, which is the firmware which we're working on, and then it comes to the compiler programming language we are developed or owned based on the open source resources from Oak Ridge National Computing. You may be familiar with the ZAC. These are middleware that accept different circuit input, including OpenQASM, CoolCirc, and they can do cross compilation, they can do transpilation, and they can run the circuit on different backend, including us. But what is unique to what we build off based on these tools is we have basically a version of Quantum MPI. So like our framework is able to talk with several QPUs, not only one, do hybrid coding and send the calculation to several classical and quantum backends. You can see an actual picture of one version of this software on the top of a stack I'm talking. We call it Quantum Emulator for QuantumBrilliance, or maybe a bit longer, QB Software Development Environment, which is HPC scalable, for short QBQE. So QBQE is currently available, and people can start experimenting with it. We think it has some unique feature compared to some of the competitors. So how does this all work really, physically speaking? So I talked about that it operates in the ambient conditions, but it's even better because we have very high qubit density. We have a simple control system, which is what allows us to build this quantum system easily. So the reason that the ambient condition is possible to do quantum computation is because of the features of the diamond. As you can see on your right, a typical carbon-12 lattice, there are these nitrogen vacancy in diamond, which is you can see vacancy in the center, and then there is a nitrogen impurity. Typically, these are accompanied by few carbon-13. Those are that gold ones, orangish ones, and all of which will provide us a qubit, a physical qubit to work with. What we are doing, which is unique to us, we have methods, in-house technology to actually put these MV center, each of these MV centers in an 2D array, engineer them, be able to control them, and the way we control them is using microwave control and optical control. What's helping us is that the technology with the microwave control and optical control is very well established and well developed compared to some other systems. So we could build a robust system and compact system, as you can see in the middle of the screen, and we have a performance that the coherence stop is above 1 microseconds. Gate times vary between order of 1 to order of 10 microseconds. And we have very promising fidelities and we're working to even improve those fidelities that you see on the screen. But quantum accelerators. So when you have graphic card size QPUs, this gives you a new vision. Yeah. So now you're not competing with mainframe quantum computers, but you can exploit the size of the systems. The first thing we want to say is that quantum is, of course, the solution. So there is limit to the capabilities of the traditional transistors. Even mainframe quantum chip shows that one quantum chip can be several orders of magnitude faster than biggest HPC resources. But mainframe quantum computing is limited, really. And why is limited? Because obviously you have that mainframe size, power, and complexity to worry about. And also the connection to the HPC center is obviously a connection that brings the latency. On your right, you could see a Google rendering of the planned million physical qubit system. This is very impressive, but the size is massive, obviously. So you are naturally only can compete with the supercomputer. You cannot compete in the edge applications. So the vision we bringing is that we think, okay, quantum mainframes still have a significant roles, which is that side of this plot you see, the left side, working with supercomputers in a specific application. And these supercomputers, they can host computers like all computers. So there could be CPUs, GPUs, and quantum accelerators inside. But if you move to the right, you can see a main roles for the quantum accelerators. This is similar to everything happened to classical computers as well. HPC computers, supercomputers still have a role, but there is a significant roles for the accelerators. And this is to used for medical applications, for data center applications, for tracking in the cars, can be equipped with satellites because they support a range of temperatures. So you could do distributed computing, and of course you could do mobile computing as well. So we believe this would be change how quantum computers are useful. We look at it as something that we call quantum utility, and I'm using the term quantum utility specifically to differentiate it with the quantum advantage. Thinking about if the quantum advantage is basically beating a supercomputer, quantum utility is about if you do better than any similar size local machine. Yeah, so not essentially supercomputers. So there is really two ways to show quantum utilities. One direction, which is upward in the streak, is the way that and mainstream computing companies like Google and IBM taken, and they were able to show outperforming one supercomputer. But we're taking a different direction, which is that we want to outperform not one CPU or one GPU. This is much easier. It's useful for edge application. And that green point there is not where we stop. It's actually where we start. And we actually improving these compact size quantum computer to be more and more. And we're going upward from that direction as well. So we're going to have the GPU size quantum cards with 50 qubits that actually can compete with large computers as well to doing useful tasks. Okay, so examples. On your right, you see a plot that actually we produce using quantum emulators. If you remember that QBQE I introduced before. In that plot, we use the 2 CPU AWS instant. It's actually 2 virtual CPUs, but 2 CPU, I guess you guys could agree with me that is the dual cores is most application in everyday computers using either single or dual core. Yeah, so that's why we use that. What we're doing, we're repeating that random quantum circuit sampling that Google as well featured in the quantum advantage paper. So this is the same randomized circuit sampling you see. So the red one is obviously the estimation for our quantum Diamond quantum computer, and the blue one is what the best in the class emulator can do. This emulator is AER. It is basically the same emulator. If you ever work with the Qiskit, same emulator that Qiskit is using, but in our system we have access to that as well. 8 GB of memory. As you may expect, the classical time for low number of QPU is better because quantum computers have a large overhead due to the initialization, due to the measurement times. However, if you fit some things on that, you clearly can fit an exponential on that and a linear curve on the red one. You see that the quantum eventually would get better. And not that you're not talking about 50 qubits, 60 qubits when things are getting better, because you're competing with just 2 CPUs and thinking about our system, you are beating in this specific case in 15 qubits. So 15 qubits, if you have on an edge application like that, 15 qubits would be enough for you to get better results with the quantum. So I prepared 2 examples. As I mentioned before, we are doing some collaborations with quantum salts, but to be interesting for everyone, I thought I choose two examples which are different applications we are actually doing with other collaborators. So these are hopefully interesting with everyone. So the vision I like you to pay attention is that these quantum accelerators can be used for massively parallelizable applications. So one example is, of course, computational chemistry. So computational chemistry is a very important application because it is the method used for material design, for battery design, for drug design, chemical synthesis, enzymes, all of these things using computational chemistry. And there is a massive demand in the industry, actually. Industries spending significant money to do better calculations. Quantum mechanical methods are very powerful, very promising, of course. The challenge is that they are computationally very expensive, these methods. So this is why that we still do classical methods such as Hartree-Fock when it comes to computational chemistry. We still do DFT for the reason that quantum methods are expensive to do. So the mainframe quantum computers, such as the papers, I'm sure some of you are aware by IBM or Google team, they were really limited to the single molecules. That's why they simulated even of the limited size. But if you have our vision and use our infrastructure with the massively parallelized QCs, now imagine you don't have one quantum chip, you have several quantum chips that they can do each quantum routines, and you can do classical calculations to connect them together. So this way we could do actually molecular dynamics, which is that picture it's trying to show you. So to actually highlight the massive demand that industry has, you may be familiar with some of these bespoke classical systems. They developed specifically to do these computational chemistry calculations. One good example is Anton system, which is at Pittsburgh Supercomputing Center. This is a supercomputer ASIC in a sense, just designed to do molecular dynamic. What we could offer here, so we could actually accelerate the sort of calculation in the literature called QMMM. So molecular dynamics, and you see that there is a picture that shows we have several classical computers and you have several quantum accelerators. If you're interested to describe the dynamics of an interesting chemical system, what you could do, the quantum accelerators can work on the individual molecules. Typically, this is called that QM would do atom geometry optimization. So QM would do parts like atomic orbital integral evaluation, or and solve the optimization problem using something like VQE. And then the classical part, it would do basically just Newtonian mechanics. So and the classical parts, they are very good in doing things like Newtonian mechanics. So we are only doing what's that classical part is weak at. We're doing that part quantum and leave the part that the classical accelerators are powerful with them. So, and the interaction potential and force field is what needs to be communicated. So this enable us to do larger scale QMMM, higher accuracy because we are employing something called full configuration interaction. So this would give you better result than DFT and Hatchie-Fock methods. And this gives you an opportunity to actually simulate electrophotochemistry. And there are actually papers in the literatures to show that. However, I don't believe, because of the limitations of mainframe quantum computer, anyone really, as a company, demonstrated that. And we are building these features into our software and also hardware layer. So QBQE will be eventually equipped with these plugins. So last example, which is supposed to show you one of these edge application, is the problem that defense forces usually faces, but it's a problem for every industry, and that's a speech to text. So imagine that the core task is that you have an audio signal or you have an image, and you want to determine that what's the most likely sequence of event that happen. So one good example is that if a voice is being transmitted and the computer job is to do this speech to text, you could of course connect to your powerful centralized computers via cloud. However, you would get correct message, but there would be some delay, and that delay it could be fatal when it comes to the defense application. If you use your edge computers, it could possibly process your audio very fast, translate it to the text. However, they are very prone to the error. They are inaccurate, and you often see that they send the wrong message. I want you to all think about these speech-to-text tools. You see them everywhere. Like if you watch the YouTube or like some TV channel, they have this speech-to-text. You would, if you review your memories, you would realize that they could work very fast, but some of the things they would translate to is actually funny because of the inaccuracy. Yeah. So computational cost requires significant approximation when you do it all classically, which increase the risk. And then network latency is also an issue. So why this is happening? It's important to think first why this is happening, because almost all mainstream methods doing a speech-to-text or similar video processing, signal processing, they're all two-step processes. One step is a machine learning step, and one step is a search step. So the machine learning step is typically a recurrent neural network, is processing these images, the signal, to actually find what we call a probability table, like a statistical time series. You can see on that picture. So they translate that signal to a table of probability. This table is typically of the massive size. Each time being has a series of probabilities, and the job for the search algorithm is that obviously to somehow search this table and find the most likely sequence of the event, the one that has the path in a sense that has the highest probability. So the computational resources required to do this explode with larger and larger audios. So what they do, what's happening is that because these probabilities have correlations to each other, so it's not ideal to ignore part of it and just process part of it. However, what is the current approach? Methods like beam search, if you're familiar with those methods, what they do is that because of the classical computation resource limitation, they just process a part of the audio, yeah, or the part of the image at one time. So what they do is that, imagine the word incomprehensible. So they do like divide that to several parts, and like I said, they have a beam width of 4. They just search like that. They try to process like that. This is the reason the results are typically fine, but when the audio is not really clear, or when there are even accents, and when there are pauses or everything, this could translate to really funny results. So we invented an in-house technology called quantum machine learning decoder, and the important thing here is that this machine learning quantum decoder, it's not a quantum machine learning device, it's a hybrid device. It doesn't have the disadvantage that you may be familiar with quantum machine learning. It's just one part that is good classically, it's still being done classically, and we only do the search part quantumly. Because quantum methods are powerful, well established, when they're doing the search. I put some numbers for you. Rafael, is it going to?
Yes, we have a couple of minutes.
Yep, yeah. Okay, I wrap it up quickly. Which actually, if you do the quantum search, you could use the Grover search, which have well established improve accuracy and speed. So I'm almost done. I was just quickly say that, look, next step for us is to do more application discovery. We want to get this co-processing software out, and then we could use the quantum accelerators for co-design and development. The last thing I want to put on the screen here is the opportunities. We are actively looking for the talent. We think we have a great team, but if you are interested to join, feel free to contact me on LinkedIn. We have a headquarters in Australia, in Germany. We're going to establish one in North America. Unfortunately, not yet South America, but hopefully we get there soon. Thanks, Rafael.
Soon. Okay. Thank you, Nariman. You are receiving claps here in the screen. So thank you very much.
That's great.
There is a question from Pablo, which is a student. Is there a price estimate for the device, maybe similar to a graphic accelerator?
That's a great question. So just noting that the graphics card size ones coming in 225, so still we're not commercializing those. But for the device that you saw, that it was the size of the 19-inch rack that is currently available, unfortunately, the pricing is just because these things are going to be negotiated with the HPC center. They want case by case by the needs of the HPC centers. And that includes the software and everything.
Mm-hmm. Well, and there is another question from Araceli. What do you think is the actual roadmap to have a diamond-based quantum computer?
Yes, so well, the roadmap certainly contains the main challenges to have a larger scale diamond quantum computer, and those challenges are about scaling. Yeah, because we already have 2 qubit, 3 qubit, 4 qubit systems, and we can prove all the basic algorithms in these systems. The question is that how you get to say 50 qubits. And this is where we think we are uniquely positioned with our collaborators. What we do is that we engineer methods to actually controllably put those nitrogen vacancy in an array on a diamond chip, rather than just like searching through to hope to find a envy center. Is about that how to engineer those in an array that they could talk to each other. So the roadmap is about the scaling up, and obviously how to control the system. But the dynamic control, things like that are better established in this area.
I see. Thank you. My final question is about a graph you showed that you think these diamond computers are going to reach consumers?
Actually, the answer is yes already, although our model at the moment is that we are integrating with the HPC centers, but maybe I wasn't fully clear. So users can talk to our system through the HPC application. So what would happen, for example, with the Policy Center, you go subscribe to their system, be a user on the Policy, and you could talk to our backend, which is just the Diamond Quantum Computing. So our systems are available via HPC centers, and hopefully in the 5 years, they will be available to be purchased separately by everyday users. This is what we think.
Thank you, Nariman. Well, thank you very much. We reached the end of the session. So we invite you all, you are receiving claps again. So we invite you all we will close this session. I will invite you all to the next one, which is the last of the day. Thank you, Nariman. Thanks again.
Thank you. Thanks, guys.